Right now, as you watch this, the most dangerous fault in the United States is moving. It is not shaking, it is not making the news. No alarm is going off in any coastal town along the Pacific Northwest. And yet, over the past 7 days, instruments buried in the ground from Northern California up into Washington have counted 2,634 separate tremors along a single stretch of the planet. 2,634 in 1 week, and almost no human being felt a single one of them. That is the strange and unsettling paradox that defines the Cascadia subduction zone tonight. The loudest signal the ground is sending is one that no person standing on top of it can detect. You could be walking the beach at Brookings, Oregon, sipping coffee on a porch in Crescent City, driving the coast highway with the windows down, and the earth beneath your feet could be straining, creeping, and shifting in a way that machines are screaming about, while your own senses tell you that everything is perfectly calm. This gap between what the instruments know and what the people above them feel is the entire structural logic of the impending crisis. Because that exact silence, that exact stillness, is how the last great catastrophe on this coast began. The data streaming from these seismic instruments reveals the systemic deficit that is quietly building beneath the Pacific Northwest. We are not talking about earthquakes in the conventional sense, sharp, violent cracks that snap in seconds and send a jolt through the rock. The instruments are recording tectonic tremor, a faint, low-frequency and drawn-out murmur. This signal originates far down at the base of the fault, in a zone where the rock is hot and pressured enough that it does not snap, it slides. But this slide does not release the system's pressure, it transfers it. As the lower section slides quietly, it takes the strain and shoves it upward onto the locked zone, the part of the fault that holds and holds and holds, bending and deforming like a spring being slowly compressed, until one day it cannot hold anymore. When that upper section finally lets go, the result is a magnitude 8 or 9 event that rearranges the coastline forever. The 2,634 tremors recorded this week are not a series of release valves. They are the sound of a loaded gun being loaded a little further. Each one is a mechanical nudge of stress handed up to the locked zone above. The numbers themselves are stark and do not represent mere background noise. While 2,634 tremors in a single week are concerning, a look at the running chart for 2,634 tremors across the year shows that this surge is trying to match or pass the last big spike from around March and April of 2026. This is one of the loudest stretches of silence the fault has produced in months, and it is concentrated. The tremors are not spread evenly along the full 1,000-kilometer subduction zone. The overwhelming majority are clustered at the extreme southern end, beneath the southern coast of Oregon and reaching into Northern California. This is arguably the most concerning location on the entire coast for such activity to concentrate. Yet, a central systemic question remains unresolved. The presence of a tremor surge does not mean an earthquake is coming tomorrow, next week, or next month. Tremor and slow slip are in a sense a normal systemic respiratory rhythm. The southern margin breathes in and out, loading and pausing year after year. Every one of these ordinary episodes, however, leaves the locked zone more stressed than it was before, as the accumulated load is never truly reset. We are witnessing a system load itself in a way that is both completely ordinary and quietly terrifying. But the final catastrophic break remains unreadable from the outside. We cannot tell whether this specific surge is just another routine breath, or whether it is one of the final few breaths before the full mechanism fails, an ambiguity that poses the central question for the future of the entire Pacific Northwest. To understand why 2,634 quiet tremors should make the hair on your arm stand up, you have to understand the machine that is producing them, and it is a machine. A slow, enormous grinding machine that has been running for millions of years just off the coastline of the Pacific Northwest, completely out of sight and almost entirely out of mind for the people who live in its shadow. Off the coast of Northern California, Oregon, and Washington, there is a piece of the planet's outer shell called the Juan de Fuca Plate, and its southern portion goes by another name, the Gorda Plate. This slab of ocean floor is being pushed relentlessly toward the continent. When it reaches the edge of North America, it does not stop and it does not pile up, it dives. It bends downward and slides underneath the much larger North American plate, descending into the planet at a shallow angle, foot by foot, century after century. This process, one plate diving beneath another, is subduction, and the boundary where they grind past each other is the Cascadia subduction zone. Along this massive contact plane, which is a gigantic slanted plane hundreds of miles long and tens of miles from top to bottom, the behavior of the rock changes depending on how far down you go. Far down at the bottom of that contact, where the rock is hot and squeezed under tremendous pressure, the two plates do not lock together. They slide in those slow, quiet pulses we call tremor and slow slip. The rock down there is too warm and too plastic to snap. It oozes. But as you move up the fault toward the surface, toward the cooler, more brittle rock closer to the seafloor, everything changes. Up there in the locked zone, the two plates are jammed together, stuck, welded by friction and pressure into a single immovable mass. They are not sliding or creeping. They are simply holding on while the ocean plate keeps pushing from behind. Because the bottom of the fault is moving and the top is not, the strain must go somewhere. Every time that lower section slides in one of these quiet episodes, it loads more force onto the locked section above it, which refuses to budge. The locked zone bends, deforms, and stores the energy like a spring being slowly compressed. For a long time, this mechanism was fundamentally misunderstood. As recently as a few decades ago, the prevailing assumption was that Cascadia might not even be capable of great earthquakes precisely because it was so quiet. The reasoning went that a dangerous fault should be making earthquakes, and since Cascadia was not, perhaps the plates were sliding smoothly past each other, releasing their stress gently. We now know that reasoning was exactly backward. The quiet was not evidence of safety. It was evidence of a fault so thoroughly and strongly coupled that it was not releasing anything at all, storing every bit of strain for a single enormous release. The silence that once reassured scientists is now understood to be the most ominous sign of all. When this accumulated strain finally exceeds the threshold of static friction, the entire locked zone will snap forward in a matter of seconds to minutes, releasing hundreds of years of stored strain in one catastrophic lurch. On a subduction zone this size, running for roughly 1,000 kilometers from Cape Mendocino in Northern California to British Columbia, that rupture is a magnitude 8 or magnitude 9 event. We have a perfect, terrible example of this physical threshold from the year 2011 off the coast of Japan, where a subduction zone exactly like Cascadia let go along the Japan Trench. The upper portion held until it failed, resulting in a magnitude 9.1 earthquake. The seafloor leapt, the coastline moved several feet to the east, and the sudden displacement of rock shoved a wall of ocean toward the shore, generating a tsunami that took around 18,000 lives. Cascadia is capable of producing the exact same mechanism, the same magnitude, and the same kind of tsunami. The relentless shoving of the diving ocean plate is already literally crumpling and lifting the edge of the continent, folding it upward like the hood of a car in a slow collision, creating what geologists call the Cascadia fold and thrust belt. Yet the average person on the west coast only associates earthquake risk with the San Andreas faults, a sideways grinding boundary that tops out around a magnitude 7.9 and cannot generate a major tsunami. The most dangerous fault on the continent is the one sitting offshore, loading silently tonight with 2,634 tremors that nobody can feel. The concentration of 2,634 tremors at the extreme southern end of the Cascadia subduction zone is not a random distribution of energy. It is the direct result of a highly complex, intensely stressed, and aggressive piece of marine geology that distinguishes the southern margin from the rest of the 1,000-kilometer fault system. To understand why this specific sector is lighting up, we must look beneath the ocean surface at the mechanical anomalies driving the subducting slab. In this southern zone, the ocean floor entering the trench is called the Gorda Plate, which represents the southern portion of the larger Juan de Fuca Plate. Unlike a clean, rigid sheet sliding uniformly beneath the continent, the Gorda Plate is a localized troublemaker. It is smaller, younger, and is being actively squeezed and deformed from multiple directions simultaneously. This internal fracturing and bending accelerate the accumulation of tectonic strain, translating into more frequent slow slip events beneath the southern coast of Oregon and Northern California. This baseline stress is further amplified by two prominent seafloor features that pump additional energy directly into this segment. The first is the Blanco Fracture Zone, a jagged transform boundary slicing through the ocean floor right up against the southern tip of the Cascadia system. The relentless lateral grinding of the Blanco zone transfers sideloading stress directly onto the subduction fault. The second feature is the Gorda Ridge, an active spreading center where new oceanic crust is being continuously generated and forced outward. This structural arrangement means the southern end of Cascadia is subjected to a triple convergence of tectonic forces, shoved from behind by a spreading ridge, ground against from the side by a fracture zone, and fed by an internally fracturing plate. Because of these convergent pressures, long-term empirical models divide the risk profile of the fault rather than treating it as a single homogeneous unit. When researchers calculate the probability of a major rupture over the next 50 years, the statistical divergence is profound. For the southern margin, the exact zone that just absorbed the bulk of this week's 2,634 tremors, the probability of a large earthquake sits between 37 and 42%. Conversely, for the northern segment off the coast of Washington and British Columbia, that same 50-year probability drops to a range of roughly 7 to 12%. This means the southern coast is approximately 4 to 5 times more likely to experience a catastrophic failure in the next half-century than the north. This localized loading pattern correlates with a distinct failure mode documented in the geological record. While a full margin rupture of the entire 1,000-kilometer fault represents the maximum capability of the system, creating a global magnitude 9 event, the southern segment possesses an independent history of partial ruptures. The mud and rock of the seafloor preserve a clear chronicle of these events. When an earthquake occurs, it triggers massive underwater landslides, depositing distinct layers of sediment known as turbidites onto the deep ocean floor. Core samples drilled from these sediments reveal that while some turbidite layers span the entire length of the margin, a significant number are isolated strictly within the southern sector. The sediment data confirms that the southern segment has its own independent rupture clock and failure cycle, allowing it to fail in magnitude 8 class events without waiting for the rest of the fault zone to reach its structural limit. Intellectual honesty demands the recognition that a single high tremor week does not constitute a definitive short-term prediction of failure. These episodes are part of the normal rhythm of the transition zone. However, the system does not reset or forget. The strain from each slow slip event stacks directly onto the pre-existing load, systematically walking the southern segment closer to its mechanical limit. While the microsignals of tectonic tremor accumulate invisibly down at the base of the fault, the macrostructure of the continent itself is responding. This is something that can be measured directly in millimeters and watched as a climbing line on a chart year after year. The southern coast of Oregon is rising right now. The land itself is lifting up out of the ocean slowly, steadily, and the instruments that track it have been logging this deformation for the better part of 2 decades. This is not a theoretical model or a predictive simulation. It is an empirical metric that establishes the physical reality of the loading process. Scattered along the west coast are highly specialized GPS stations bolted directly into the bedrock, engineered to detect crustal movement down to the millimeter. One specific unit, located near Brookings, Oregon, sits directly above the southern locked zone that has absorbed the bulk of this week's 2,634 tremors. The vertical data from this station is unambiguous. Since its record began in 2008, the coastline in this sector has risen on the order of 60 millimeters. To evaluate this metric accurately, we must deconstruct any superficial interpretation of what vertical land motion implies. A rise of 60 millimeters, roughly 2 inches, might seem negligible to a casual observer, but when applied to a continental margin, it represents an immense volume of displaced mass and accumulated mechanical energy. This uplift is not driven by volcanic inflation or magma swelling beneath the surface. There is no filling magma chamber beneath Brookings. Instead, the land is rising due to elastic deformation. As the subducting oceanic plate dives beneath North America, the high-friction interface of the locked zone drags the overriding continental plate downward and forward with it. As the edge of the continent resists this downward pull, the crust bends, buckles, and bows upward like the tip of a diving board. The 60 millimeters of recorded uplift is the direct measurable proof that the continental crust is acting as a massive spring being slowly compressed. This surface deformation connects mechanically to the tremor counts at the base of the fault. The tremor surges and the coastal uplift are 2 distinct manifestations of the exact same tectonic engine. Down below, the hotter portion of the fault slides, transferring its strain upward into the brittle locked zone. Up above, that locked zone flexes under the newly transferred force, pushing the coastline higher. The system is being wound from the bottom and confirmed from the top. The structural danger of a compressed spring is that its deformation is temporary. The crust will only store this energy until the strain exceeds the threshold of static friction along the locked interface. When that critical limit is breached, the mechanical process reverses instantly. The land that has spent centuries bulging upward will snap back down, dropping by a meter or more in a matter of moments as the bent rock springs back to its equilibrium state. This sudden, violent subsidence of the seafloor and the coast is the exact mechanism that generates a local tsunami. The abrupt displacement of the overlying water column forces the ocean outward, sending a massive wall of water directly toward the nearest shore. Because the fault line sits just off the coast, the travel distance is minimal, reducing the warning window for residents to mere minutes. The same structural nearness that causes the Brookings GPS station to log 60 millimeters of uplift today is the exact geographical factor that eliminates a comfortable evacuation window tomorrow. The statistics, the tremors, and the rising coast are 3 independent data lines pointing toward a single physical reality. The spring is loading, and its ultimate unloading is a fixed mechanical certainty. The modern instrumental records we monitor today, the 2006 and 34 tremors and the 60 millimeters of coastal uplift, represent a very brief snapshot of a much larger historical loading cycle. To grasp the true volume of energy stored within this system, we must look back to the last time this compressed spring fully released. For centuries of modern history, the absence of a written seismic record along the Pacific Northwest led to the superficial assumption that the Cascadia subduction zone was safe, peaceful, and perhaps entirely incapable of producing major earthquakes. This historical narrative has been thoroughly deconstructed by a precise assembly of geological and empirical data gathered from both sides of the Pacific Ocean, revealing that the historical silence was merely the signature of a completely locked fault accumulating strain. The primary physical evidence was discovered within the tidal flats and estuaries of the Pacific Northwest coast, where researchers identified ghost forests, stretches of ancient cedar stumps standing dead in saltwater marshes. These trees once grew on dry land but were abruptly killed when the soil beneath them subsided below the tide line, drowning their root systems in seawater. Tree ring analysis proved that these forests died simultaneously, pointing to a sudden, massive coastal drop rather than gradual erosion. This sudden subsidence was accompanied by extensive sand sheets layered directly over the drowned forest soil, providing a clear physical fingerprint of a massive tsunami that swept far inland at the exact moment the land collapsed. To determine the precise timeline of this rupture, scientists matched these coastal records with historic documentation from Japan. In January of the year 1700, Japanese coastal villages recorded an orphan tsunami, a series of destructive waves that struck the shoreline out of a calm sea without any preceding local earthquake or shaking. By correlating the tree ring data from the American coast with the precisely timed records of the orphan tsunami in Japan, the structural timeline became certain. On the night of January 26, 1700, the entire length of the Cascadia subduction zone underwent a full margin rupture. The fault unleashed an estimated magnitude 9 earthquake, dropping the coastline, drowning the forests, and sending a wall of water across the open ocean for 10 hours until it slammed into Japan. This geological data matches the oral histories of the region's indigenous peoples, which describe violent nighttime shaking, the destruction of coastal villages, and the ocean rising to swallow entire communities. The historical reality of the 1700 event serves as a direct preview of the mechanical limits governing the West Coast today. The fault loading right now is the exact same machine that failed 3 centuries ago. The system has been continuously storing strain for 326 years, with the subducting oceanic plate driving relentlessly into the continent with nowhere for the energy to go. While the average recurrence interval for these great earthquakes is roughly 500 years, the turbidite record of underwater landslides shows that the intervals fluctuate significantly, placing the modern coast squarely within the historical window of a potential failure. The 2,634 tremors tracked by our instruments are not an isolated anomaly. They are the early silent phase of the exact same physical cycle. We are the first generation of humans who possess the tools to observe this subduction zone load itself in real time, transforming what was once invisible strain into measurable data lines. The ongoing accumulation of pressure at the base of the fault and the steady deformation of the land above it demonstrate that the system is operating under strict mechanical limits, moving steadily closer to an inevitable structural reset.